this morning's subject is how much energy could be conserved by changing the pipeline systems that are used to transport the water from wherever the water source is to the water distribution system and out the end. I know that there are other types of systems out there, but this morning's conversation is going to be primarily with pipelines and center pivots. There are procedures for doing systems that might be tow line in nature or solid set as well that can be used. And I'll try to point out a few things along the way as we go here. Before we get started into the meat of this, though, I wanted to mention a couple of publications that, or at least one that is available through a Midwest Plant Service out of Iowa State that deals with sprinkler irrigation systems, and it covers the subjects all the way from management to hydraulics and sprinkler selection, the whole gamut of things. The title of it is Sprinkler Irrigation Systems. It's Midwest Plant Service 30, available through the Iowa State Distribution System. So if you type on Google MWPS-30 Sprinkler Irrigation Systems, you should be able to get to the point where you can order a copy. They're $25 or $30. The publication was done in 1999, but most of this material has not changed at all. We've got some new systems out there, but other than that, the guts of it are going to be the same regardless of when it was published. So just some idea there. Also on the internet, there are obviously sources for some of the material that we're going to talk about this morning. So I've been using this slide to start each one of these presentations dealing with the water side of things. And this morning's subject really is going to deal with the one over on the far right that's going to be pumping pressure. And this, basically applies to all different kinds of irrigation systems. I have it as pivots here. We tend to be more pivot oriented down in Nebraska than anything else, and so that's where that's coming from. But basically it's the pumping pressure that we have to supply to get the water distributed through the irrigation system. The outline for this morning's discussion is going to be, we're going to talk a little bit first about just decreasing the operating pressure of the system and how we can estimate how much energy can be saved from that perspective. And then we're going to talk about some hydraulics in terms of pipeline designs, friction loss estimation, and lastly, just some real quick and easy cost comparison kinds of things to compare a couple different types of systems that we're going to go through this morning. Meant for this to be animated, but if you look at a system that might have a pumping depth of 200 feet, these lines that are on here are curves that are pumping cost. If the irrigation pump is at 80% of the performance criteria, if we're pumping at 20 psi, you can see that we're going to be using somewhere around $1,450 to put an inch of water on. If we're running at 60 psi, that number is up around 2,000. So you can see that actually, I guess it should really be closer to $1,700 if we're at $4 per gallon diesel fuel. The bottom line is there's a fair cost involved in putting an inch of water on these days, and so just altering the pressure of the system can make quite a bit of difference. So let's go through an example here. If we have a system that's pumping from 125 feet, pressure at the outlet is 70 psi, 130 acres, 12 inches of water applied per year, $4 per gallon diesel fuel. The way that we've been doing this, or we did it when we were talking about the pumping plant, is one way, quick and easy way to figure this out. At 70 psi and 125 feet of lift, this chart would say that if we were at 100% of the Nebraska pumping plant performance criteria, we should be able to put that inch of water on utilizing 2.61 gallons of diesel fuel per acre inch. So if we use that number and multiply by the total number of acre inches pumped, you can see here we have the calculation of 130 acres times 12 inches. to get us that 1,560. Doing the math would say that we should be able to do that with a little over 4,000 gallons of diesel fuel at $4. That turns out to be about $16,000 of cost to pump that water on to put 12 inches on a full 130 acres of field. And if we were to compare that with the energy cost, then to put the same amount of water on the same area, everything the same except for the outlet, the pressure at the pump outlet now dropped 20 psi here. We go back into our chart, and we can see that now instead of 2.61, we should be able to do it with 2.19 gallons of diesel fuel per acre inch. And again, we do the same mathematics to get the total number of inches applied. And when we multiply that out, you can see that now we're about 600 gallons or so less diesel fuel use, and about $3,000 or just shy of $3,000. We'll come back to the exact numbers here as we go along, but the total fuel cost would be less in this scenario. So if the field conditions were right and the system had been out there for a while, we might run into a scenario where we have relatively high operating pressures on that system, and by putting the new sprinkler package on and in most cases making some adjustments in the pump, we can reduce this overall cost of pumping that water on an annual basis quite significantly by just reducing the pressure at the pump outlet. We can't do this just unilaterally. There's the other things, the sprinkler package, or dealing with the pressure requirements of the system, and making sure that the new pump setting is at an efficient point in that whole operation. So if we look at then the cost comparison here, in terms of what we might save, the 4,072 gallons for the existing system, $16,286. The new one, if we reduce the pressure to 50 psi, would be the operating cost of $13,666. So the potential energy savings, since that's the topic of conversation really here in this series, is 656 gallons of diesel fuel for that particular system. If we convert that then to dollars, you can see about $2,600 of savings per year by reducing this pressure. So now if we go back and look at what we might have to do to make this work in an efficient manner out there in the field, we want to know how much we can spend a day and that will pay back a loan. And so just like we did with the pumping plant stuff earlier in this series, we want to know what the time value of money is. And so we use a series present worth factor basically that converts a series of 5 or 6 annual payments to what we could spend today as an initial investment. And this chart is in the PowerPoint, obviously. And let's say that we can borrow money from our lending institution for 8% interest, and we want to pay this loan back in 6 years' time. So we have a present worth factor here of 4.62. If we then multiply our $2,600 by 4.62, you can see that we could spend $12,000 today and pay off our loan in 6 years with the savings. So that means that we have $12,000 to make adjustments in the pump and potentially change the sprinkler package that's out there in the field. So these are the kinds of things that one can use to visit with producers in terms of where the dollars might be. I think this is a point which we can stop and deal with questions up to this point. Do we have any questions from the group yet?
No, we don't.
Okay. Let's move on, and we'll move into how we estimate the friction losses in various parts of the system. So we start with some basic hydraulics, and the energy available in the water is both kinetic energy, water in movement, and potential energy that has to deal with elevations of pipelines and water pressure inside the pipeline. So if we want to do this from a overall comparison of one position in the field to the other, we need to account for the velocity, the elevation, and the pressure head. However, if we're wanting to just look at the friction losses in our system, we really don't have to deal with some of these things, the elevation head and the pressure head necessarily. And the reason for that is that unless we change the field situation, the elevation head is going to be the same regardless of whether we start with one system or another. And if our system requires 50 pounds of pressure, that pressure is not going to change by changing the pipe that we put out there to distribute the water. So take a look a little at some pumping installations here. We had this in the pump part. And if we look at the elevation head here, this is how far we're raising the water from the pump inlet to the sprinkler distribution system. The pressure head is the pressure in the pipeline that we need to operate the sprinkler at the end. And we're going to spend most of our time talking about the one that's on the top there, the friction loss component of this particular drawing. Likewise, if we do this on a deep well turbine situation, we have our lift here, which is how far we have to move the water from the groundwater to the midpoint of the outlet, and then what kind of pressure we have at that outlet point. So again, we have the total dynamic head that includes the friction loss that would be in the system. And we're going to talk a bit more about that. The way we utilize before we get to there though, the way we utilize velocity is to ensure that the pipeline design is adequate in diameter so that we don't develop issues related to pressure surges associated with things like water hammer. So the calculating of velocity and velocity head is really just to verify that the design is good. And if we look at this scenario here, we still have the we have PVC pipe at 125 PSI rating. Diameter of that, at least from one type of pipe, was 8.095 inches inside diameter, a flow rate of 850 gallons a minute. If we do this, the flow velocity determines how much energy is in the water, or part of that. It'll determine the friction loss that we're going to calculate in the pipeline. And as I was just saying, we're going to use it initially here for design compliance in terms of the velocity, the maximum velocity we'd like to see in a pipeline. So to do this, then the pipeline velocity here really is the flow rate divided by the cross-sectional area of the pipeline. And a simplified way of doing this is just to utilize the equation that I have here on the screen of 0.409 times the flow rate divided by the diameter of the pipeline squared. This accounts for the fact that the inside area, cross-sectional area of the pipeline includes pi, and so I've already dealt with that in the 0.409 kinds of things. And so if we go back then and utilize the numbers that we had in our given here of 850 gallons a minute and actually it is supposed to be a 095, not 8.8095. The answer here is correct to 5.7 feet per second. Now, the design criteria tends to be we should try to keep the flow velocity in the pipeline less than 5 feet per second. In this case, we're at 5.7 feet per second. And really whether we're going to develop water hammer in these scenarios really depends on how the pipeline is set up. If we have a quick shut-off valve in the system, we're going to have one thing. Likewise, if we have a long, 2,000 or 3,000 feet of pipeline that this water goes through and we suddenly shut the water off, we have opportunities for water hammer. So to some degree, this velocity is higher than we'd like to see it, but if we have short pipelines or ways in which we can deal with the surges in pressure like sprinklers and pressure relief valves, we can tend to deal with some of these things quite easily. In fact, when we get around to doing some of these calculations, this 5.7 is fairly common in a much small, in fact, it's higher than this in most center pivots that are out there in the field, at least for the systems we have in Nebraska. Now, the velocity head here is a calculation in terms of what the energy is in the field, or in the pipeline, I'm sorry. And so, in this case, we want the velocity head, which is the velocity squared divided by 2 times gravity, the acceleration of gravity. And we put the numbers that we had from the previous of 5.69 divided by 2, and gravity in this case is 32.2 feet per second. We put those numbers in. We can see that the head that we are developing due to velocity head here is 0.5 feet. And if we were doing an overall energy balance in the pipeline from one position to the other, we would consider this, but even in that case, this number is so much smaller than most of the other things that we deal with. A lot of times velocity head is deemed equal to 0 and just more or less ignored. So unless you have a really high velocity system here, much higher than what we're dealing with in most of our designs, if we're done right, the velocity head is not a real significant player. Whoops, I went the wrong direction. So we just calculated the velocity and velocity head. Let's move on to some friction loss formulas here. In fact, I guess maybe this is another place if we have, we can go through this friction loss formula first. There's 2 ways in which typically we calculate friction loss in the pipeline or head loss. In this case, the Darcy-Weisbach equation was developed way back in the early stages of all these pipeline systems, and basically it now utilizes a friction factor F. It involves the length of the pipeline and the diameter of the pipeline, the L divided by D, and it involves the velocity head that we just talked about in terms of what's in the pipeline. The difficult part of this is that the F factor here involves a determination of whether the pipeline flow is laminar or turbulent, and this is basically a factor of the velocity in the pipeline and Reynolds number and viscosity of the fluid, and so it involves a bit of iterative calculations in some ways in order to get output. And so initially when a lot of this work was done, the calculation procedure was such that it made it more tedious to do, and so people moved on to a little bit of a different approach. This tends to be the most accurate in terms of head loss per 100 feet of pipeline, but really, if you look at the design criteria that people are using on the field, it's not the one that is typically used. The one that is more commonly used is this one, the Hazen-Williams equation. And again, this is head loss per 100 feet of pipeline. In this case, we have 100 divided by C, which is a pipeline. The C is a pipeline factor in terms of the roughness of the inside of the pipeline. We have Q here, the flow rate in the pipeline, diameter D on the far right, and both of these equations are empirical in nature. The assumption here is that the velocity in the pipeline is less than 10 feet per second. If we get above 10 feet per second, then we really should use some other thing. The other part of it is it's good for water only, and really this is the one that is, as I mentioned, is most widely used by the irrigation industry in terms of laying out pipelines and deciding approximately what the friction loss is in that pipeline. So before we get into an example here of the center pivot and that, any questions in the group up to this point?
No, I think you're good.
Okay. So let's move on then. We look at friction loss in a center pivot. The things that are involved here is that the discharge coming out of the pipeline is not uniform. It increases with distance from the pivot point because the pivot is irrigating more acres on the outside end than closer to the pivot point. And so it presents some hydraulic analyses that are different than the pipelines in general. In some cases, the spacing between the sprinklers may not be constant, which is another one of those assumptions in some of the equations used to calculate friction loss in a center pivot. The flow rates per sprinkler are not constant because they typically have more irrigated area on the outside, so the size of the opening goes up. And if you look at the sprinkler packages that are out there today, you'll note that the size of the opening goes up as it goes out. The wetted length of the system may extend beyond the end of the pipeline, and so there's a bit of things related to the area irrigated that comes into play in terms of doing these calculations. Now, if we look at standard pipeline or sizes of pivot pipeline, these are the range here in the first column. You see the picture on the left, but we're going to be dealing with galvanized pipe here this morning. If these pipelines are aligned with polyethylene or aluminum, the calculation is the same more or less, but there's different coefficients are used. You see the inside diameter here to the tenth or thousandth of an inch, or in millimeters if you want to do this in metric units. But typically, center pivots the standard unit is going to be 6 5/8 inch diameter, the third one down. And our example this morning is going to utilize that one, and then the 8 5/8 inch one that is further down. So if we look at a center pivot here, and we have 6 5/8 inch pipes on all pipeline on all the span. We have our 850 gallons per minute going in to the center pivot that's going to be distributed. The span lengths here really don't matter too much. It's just a layout that I put together some time ago. But this system is 1,320 feet long to the end gun or to the far right here, and we're utilizing that 6 5/8 or 6.375 ID pipeline. If you look at the distribution of gallons per minute coming out of these systems, this is what I was referring to when I was saying that the flow rate is not distributed linearly out. It's based on the area, so it's a square in the number because of the diameter squared. And you note that even out at 1,000 feet, we still have almost half of the flow in our pipeline is still there. So the last 300 feet get a lot of water, I guess is what we're getting at here. And just to kind of graphically depict what's going on in our pipeline. And so if we do the friction loss here, we're going to have a range of flow rates. And if you look at this, the way that the calculations are made, we'll get back to this here in just a second, but we have the length of the pipe and diameter all done, but the flow rate here is the variable. And if you do this correctly, you would actually use an integrated approach to this calculation, but we're going to use a shortcut that is used commonly for these kinds of scenarios. So center pivot losses. If we go back to our Hazen-Williams equation that we started off with here, and now I actually have the variables defined here in this particular slide, and we start to look at where we're going to get these variables that we fill in here. But the bottom line is, the bottom one here is no water exits this pipeline. In other words, we've got water flowing through the pipeline here from one end of it to the other. And it's the same flow rate throughout. And basically, it doesn't exit the pipeline until it gets to the very end, is what this no water exits the pipeline means. So for galvanized steel, these are C values that would go into Hazen-Williams. And in some cases, there's a range here in these values. So it's not uncommon to use the mid-range unless you've got some actual information that causes you to use one or the other. In this case, we've got galvanized steel in the range of 135 to 145. And what I've done in my example here is to take the middle one of 140. And so the C factor that I'm using in these calculations is 140. We have the 850 gallons per minute, 6.375 inside diameter of the pipeline, and there's no outlet. So what comes in goes out. If we put the numbers into the equation here and do the math, we come up with the friction loss in the pipeline per 100 feet is equal to 3.57 feet of head. And typically we do this in feet because that's the number that goes into the water horsepower calculation. If you want to convert these to PSI, you just divide this number by 2.3, divide it by 2.31, and that'll get you the PSI per 100 feet if you want to do the calculation that way. And I've got an example of that here in this little bit that I'll show you. Now, because we have multiple outlets in this pipeline, the shortcut here is rather than to integrate this equation from 0 to 1,323 feet, we utilize a shortcut here, and that's referred to as the hydraulic length. And so we have our friction loss that we calculated at 3.57 feet per 100 feet with no outlets. And now because of outlets, we have to make an adjustment. And that adjustment is made by using this hydraulic length, which is equal to the total length of the pipeline multiplied by how much water is coming in divided by Q sub B. In this case, Q sub B is just the flow rate coming in minus the flow rate of the end gun. And so that's done over on the right-hand side over here for Q sub B to get 775 gallons per minute. If we put the numbers in the equation here, we see that the pipeline, the hydraulic length of the pipeline is actually longer than the pipeline itself. And this will happen because because of the fact that we have water that flows in this pipeline at a higher rate almost all the way to the end. And so the hydraulic length here is a way of getting at what the equivalent length of pipeline would be with the outlets in place. So we go back then, and there's the equation for friction loss then for our center pivot as a whole would be utilizing that friction loss per 100 feet here that we calculated earlier, multiplied by a factor that is for multiple outlets of the pipeline, and then multiplied by our hydraulic length that we just calculated and divide by 100. So if we have a center pivot with an end gun, we utilize the F sub P factor of 0.56. If we don't have an end gun on the system, we use 0.54. And so you can see that because the end gun is there, we have more water flowing all the way to the end of the pipeline. This factor is greater than one without the end gun. So again, if we do the math here, we end up with the friction loss in terms of feet of head of 27.7 feet in this center pivot. Now, again, if you divide this by 2.31, which I guess I have here, you can see that if we have 850 gallons a minute going into the pipeline with an end gun at 75 gallons per minute, our estimated overall pressure loss due to friction is 12 psi. 12 psi. So the 0.433 here factor is really 1 divided by 2.31, so it's the same thing as dividing 27.7 by 2.31. So in this case, if you have the higher flow rates, you're going to have a fairly substantial friction loss in the pipeline that has to be supplied by the pump in order to keep the pressure at the sprinklers at the level it's supposed to be. So the other possibility is here, and one thing that people, when we get to longer systems in particular, quarter-mile systems, rarely comes into play. But if we start getting to 1,600 feet, 2,000-foot systems, it's not uncommon to think about multiple size pipelines on the center pivot itself. So let's go through an example of how this would work. And I'm still going to use the same flow rate going in here, and the same length of system, but suffice it to say that it probably wouldn't happen unless you had a longer system to deal with. So we have the first three spans are now actually, in my example, I'm using 8 5/8 inch pipe, not the 8 inch that I have here. And then the last four spans are the 6 5/8 inch line. And so the idea here is that you reduce the friction loss on the first three spans and allow some water to leave the pipeline through the nozzles or sprinklers to get it down to a flow rate where it's more, the friction loss in the last four spans is a more manageable number. Now, I've chosen the first three spans here in real operation. One would go a little bit further in length here than what I've done. It's a cost comparison between the cost of the 8 5/8 inch line versus the friction loss savings that we're going to get. And we're going to kind of talk about the savings in energy here of doing this, but what I don't get into is the cost of the pipeline that's going to be incurred by putting the extra or the larger diameter pipeline in the system. So in this case, we have the friction loss that we calculated initially, but we have it where our scenario here of 8 5/8 inch pipe for the first three spans and 6 5/8 inch for the last. And so we utilize what is referred to as a K-dual, and again, this is a shortcut that gets us a pretty good estimate of the friction loss without having to go through all of the integrated kinds of calculations that you would do if you did this correctly. And so we have a factor here, the K-dual, which is the reduction factor due to the different size pipes, and we have the friction loss in the original pipeline, so in the small pipe. So if we go through an example here, the K-dual here, if you look on the far left-hand side here, we have R divided by L. So this is, R is the length of the system that now is going to be the larger pipeline size, and L is the full length of the system. So in this case, we have the first three spans would give us 482 feet of pipeline divided by the 1,323. You end up with a number that's down in here. And we'll get a factor that actually is calculated as integrated value between a couple of these that we're going to utilize in the calculation here this morning. But these are linear, so you can integrate in between them. Interpolate, I mean, not integrate, interpolate in between them to get the exact value of the K-dual that we need to use. So the friction loss with only the 6 5/8 inch pipe was 27.7 feet for the whole system. The K-dual factor turns out to be, you utilize the R over L of 0.364. You get a K-dual of 0.67. And actually I did integrate or interpolate that value to get the 0.67 here. So to get the friction loss in this dual kind of pipeline system, you take 0.67 times the 27.7, and you see that we have 18.6 feet of head or 8 psi. So this would be the reduction in friction loss that would be in this pipeline would be a bit less than, or about 10 feet of head less for the system than previous, or 4 psi if you want to look at it that way. I think maybe we're at a position where we can maybe take a question or two if there are some.
This is Sue. I've got a question as to whether there are tools out there that we could use for those of us who aren't that familiar with the formulas and following it. Are there spreadsheets available for us to use to do the calculations?
That's a good question, Sue. And there are calculators online that'll do this. typically, our extension faculty have not gotten involved in these kinds of designs, at least not in Nebraska. And so we don't really have one that we deal with specifically. The math is pretty straightforward, so one could easily develop your own spreadsheet to do this with. But there are calculators online. If you type in Google friction loss, and I'm sorry I don't have specific examples, URLs to go to, but there are calculators out there. Scott, I don't know if you have one in your system that goes through this specifically, but
I don't have one that's specific, although the USDA tool, this is incorporated into it. For that one, you actually enter the pipeline sizes and stuff.
Right.
And, it calculates it in calculating the pressure loss. I'll have to look at that tool because I'm not sure if that will handle. I think it'll handle different pipeline sizes as well.
Scott, do you have a link to that you could put up in the chat pod?
Yep, I'll type it in.
Okay, great. Thanks.
Anything else before we move on?
I don't see anything in the chat pod.
Okay. So the last part here is to look at, how much energy can be saved and what the cost, how much money one could spend to make these changes if they were out there. And basically it's the same procedure we've used for all of the others. So if we want to compare the 6 5/8 inch pipeline for the first 3 spans and 4 spans of the smaller pipe to one that is completely 6 5/8 inch pipe, the friction loss that we calculated here was 27 feet of head for the 6 5/8 inch only, and the multiple pipe diameters were 18.6 feet of head. So that's for the center pivot itself, and we'll come back to those numbers. And the next part would be the main line distribution line to get the friction loss, to get the water from the source to the center pivot or to the distribution system. So if we look at this now in a situation, an example where we have a pipeline that goes from our source of water, whether that be a well or a surface water impoundment, that's 1,500 feet long, and we're utilizing 125 PSI pipeline. This pipeline includes 4 90-degree elbows because we take the water subsurface to get it, the pipeline subsurface to get it to the center pivot, and we have a gate valve at the pump outlet that allows us to control flow to this system to some degree. Not to say that the gate valve is a common kind of fixture in these systems, but just to give you an idea of how you would calculate a little different kind of component to the pipeline. So again, we have the steam flow rate of 850 gallons a minute, and our pipeline is 8-inch diameter. In this sort of scenario, you're more likely to see 6-inch diameter pipeline, but I'm utilizing a little different thing here. But so we want to find then the friction loss in this 1,500 feet of pipeline, and we also want to get an estimate of what the friction loss is going to be in the elbows and in the gate valve. So to do this, there are tabular values available online. I got these off of the Diamond Plastics pipeline, and I should have put the URL here, but if you type in Diamond Plastics Corporation, you'll be able to get a table like this. There are tabular values like this in numerous publications around that give you the friction loss per 100 feet of pipeline. Now, there's a couple things about this table, and sometimes you'll see these ratings in the PSI ratings that you see across the top here. Other times you might see an SDR rating, standard dimension ratio kind of rating at the top. The bottom line is that the different PSI ratings are going to have different wall thicknesses, so the inside diameter of the pipeline is going to be different. And on the bottom here, you'll see some numbers that are highlighted. So if we have and this has to do with the inside pipe diameter, if you look at the 100 PSI pipeline, it's going to have a larger inside diameter. So the highlighted values are the flow rates at which we reach the 5 feet per second design criteria. And so if you remember our calculation, when we used 850 gallons per minute, we had 5.69 feet per second. So we're beyond, below where we have a greater flow velocity than what the design maybe should be. But utilizing that factor, assuming that the potential for water hammer and other things have been dealt with, the criteria here, our number we pull off for friction loss is going to be 0.999 feet of water per 100 feet of pipeline. So the other thing we're going to need is the equivalent length of pipe for our elbows. And you can see here for an 8-inch line at a 90-degree elbow, the equivalent length of pipeline is 20 feet. So we'll do a little math with that number here in a little bit. And that involves, let's start with the pipeline itself, 1,500 feet times 0.999. And since this is friction loss per 100 foot, this 0.999, we have to divide by 100. And so we end up with basically 15 feet of head friction loss in that PVC pipeline of 1,500 feet long. Now the 4 elbows, we utilize that same 0.99 factor because we've got the 8-inch line. And this is the factor off of the equivalent length of 20. So we have 4 of those. We also have 1 gate valve. And if we look at the gate valve that's open here, 8-inch line, we have a 4.5 number that we were going to use in our calculation. And so that's there. We add these two together, divide them by 100 feet. And you can see here that the minor losses here in this pipeline are 0.84 feet. So in essence, what we'll do then is add those two together to get 15.84 or 15.8 feet of friction loss in this pipeline. Now, if we look at a scenario where we actually change our pipeline diameter to 10-inch pipe, you go into a different table. And again, we have the PSI ratings across the top of this table, and you can see what happens as we go to 10-inch and what happens to the friction factor that we're going to use. We go horizontally across from our 850 gallons a minute to the 125 PSI pipe, and now we're talking about a friction factor of 0.342. Likewise, if we utilize these inside equivalent lengths here, the 10-inch diameter is going to run 25 feet, and our gate valve is 5.5. And actually, these were, we'll utilize those factors for this calculation here this morning. Again, so we have the 1,500 feet of pipeline, our friction factor of 0.342 here. So now instead of 18 feet, our friction loss in the pipeline is 5.1. And if we do the same math with the equivalent length down below, and actually I didn't change these numbers and I should have in this equation, we end up with 0.29. I believe this math is correct even though my other numbers are not. So if we move the 10-inch pipeline, you can see that we reduced our friction loss quite a bit. So just to add them up then, for the 6 5/8-inch pipeline and our the 8-inch delivery line and the 6 5/8-inch pipeline for the center pivot, if we add these up, we end up with 43.5 feet of head, or a little over, right at 20. Right at 20 psi loss. Now, the reason for the pipeline going to a larger size was really 2 things. I think one is to deal with the velocity in the pipeline to get it down below the 5 feet per second. The other part is this friction loss that we're going to be calculating here this morning, or are calculating. And and there's potential energy savings by having the larger diameter pipe. What I'm not utilizing and will not be talking about here this morning, I forgot to mention this, but obviously the pipe costs a different amount depending upon whether you have 8-inch line or 10-inch line. So eventually the producer would, if they want to talk to them about changing these diameters of what's out there in the field or in the design criteria, you have to compare the energy savings that you might expect over a 20 or 25-year period with the installation costs that you're going to spend today. And so a little bit of an additional comparison compared to what we're going to do here this morning to get at the actual cost comparison between these two installations. But the idea is to reduce the velocity in the pipeline and reduce friction loss. So if our main system of 8-inch delivery and 6 and 5-inch in pipe is 43.5 feet of friction loss. Now, when we went to the 10-inch delivery line and multiple pipeline diameters in our system, you can see here that our delivery line dropped down, and so now we have about 24 feet of total friction loss in this system to get from the pump outlet to the end of the end gun. I got to animate the last part. We go back to our water horsepower calculation and put the numbers in. If you remember, the P is our pressure at the pump outlet, and we're going to use the shortcut approach here for this part. And then plus the lift here, we're basically going to not utilize that part in our shortcut. But if you did this whole calculation, this would be how we would do it. We'd take the total dynamic head times the flow rate times the hours of operation per year times the fuel cost. Divided by 3960 and the Nebraska Pumping Plant Performance Criteria to get us to the right numbers. Now the shortcut here is that we're not, we can go through all the math in terms of going through the hydraulic, total dynamic head and add the friction loss to it, that kind of thing. Or we can just look at the difference in friction loss, because that's really the difference that's going to happen here in this pipeline between the 8-inch and the 10-inch installation. So if you look at the second equation here, we have the friction loss for the 8-inch minus the friction loss from the 10-inch, and the difference between those two is really the difference in pumping cost that the system might expect to have. So we still have the same flow rate. We're going to have the time and fuel cost here. So our calculations said 43.5 feet of head loss due to friction in the 8-inch line with the 6 and 5-inch in pivot, and the 10-inch delivery line and the multiple diameter pipelines on the pivot were 24 feet of head. And let's say we run our system for 1,000 hours per year, and the fuel cost is $4 per gallon. If we do this math, we'll end up with the total cost differential between these two installations on an annual basis. And that number comes out to be $1,342 per year. And again, this is what would happen on an annual basis, and it may or may not be something that is worth making a piecemeal sort of installment on making improvements on the system. And so we want to know what we can spend today and get back over a period of annual savings that would total up to this amount. Again, these calculations don't include the pipeline installation cost or the pipeline costs themselves.
Could I just break in for a minute here, Bill? We've got a question as to why should a larger diameter pipe fitting have a higher friction loss?
And actually, we've got more surface area there, but the friction loss it actually should be the other way, and so I'm a little bit scratching my head here trying to figure out why it should be as well. But these are calculations that are based on velocity head, and so the velocity head should go down, and we should actually have friction loss that's less. And so I'm going to have to change this slide, I think, that's on there, and maybe the calculations as well. But I've used this example. It was actually on a training program on a national level, and not exactly sure why I ended up with those values the way they are. So I apologize for that for those who are involved this morning. I'll get that changed.
Okay, well, that's a good clarification. Great.
Again, we have the $1,342 for annual cost, and we want to know what we can spend today. So we go into this series present worth factor table that we utilized before, and the example I used is a little longer term in nature, 10 years, and if we have the 8% interest, 6.71, and again, we do the math, 1342 times 6.71, we end up with $9,000 worth of potential investment that we could make today and recoup over a 10-year period. So these would be dollars that would be utilized to change the pipeline diameter and also potentially change the pump, change the sprinkler package, those kinds of things. And this is really why, I mean, these dollars, this is might seem like a fairly large dollar amount, but if you start having to change the pump and put on a different sprinkler package and change the pipeline to boot, you probably wouldn't get these dollar amounts back. And so it's part of the reason why this sort of thing is dealt with from the beginning, and it's much easier to design the system with the right size pipeline or a larger size pipeline and get this job done right from the beginning, rather than coming in after the fact and changing pipeline diameters. It's just a much more difficult thing to deal with after it's already there. Okay, so just kind of summarizing this morning, and really in most cases the most significant energy conservation possible for people running these systems is to change the pressure that the sprinklers are operating at. And that's true of whether we utilize a solid set or a center pivot. If we can reduce the operating pressure that we supply to the sprinkler, we're going to save a fairly substantial amount of energy. Velocity in the pipeline is a criteria for the original design, and we'd like to keep that number less than 5 feet per second. But I can tell you that there are a ton of systems out there with velocities that are 6 and 7 feet per second. And because of the sprinklers that are on the system, they deal with it just fine. Where we run into issues if we have long distribution pipelines that have a lot of water, because this is the momentum thing. If you get a lot of water moving in one direction and then stop it, it tends to not react very well. Pipeline friction losses, we typically are going to estimate using the Hazing-Williams equation or tabular values to come to the same sort of thing. Mainline and minor friction losses can be used as a way of looking at what kind of energy can be saved by changing that sort of installation. And we really eventually get around to how much energy we can save in terms of pumping the water, in terms of comparing these kinds of installations.